Hi, everyone, and welcome to another power system analysis class. In the previous class, we concluded transformers, different type of transformers, and also we started with admittance and power flow and how we measure admittance, which is a big part of how we calculate power flow as well. Now, we learned that we can create an admittance matrix, and knowing the voltage and the admittance, we can calculate the current, or knowing the current and the admittance or impedance, which is the reverse of the admittance, we can calculate the voltage. Today, we will start with power flow, how we measure power flow, and if we have time, we would solve some practice problems on Gaussian iteration and how we find and calculate power flow using Gaussian iteration equations. And if we have time, we would also start with slack bus as well. Now, in power flow analysis, we usually neither know the complex bus voltage nor the complex current injection. But we usually know the complex power being consumed by the load and the power being injected by the generator plus their voltage magnitudes. This is for traditional, by the way, grids. In smart grids, everything is connected. We have a two-way connection. So most of the time we exactly have a good picture of how much the load is consuming and acting, the voltage, the current, everything is shared. But in traditional systems, again, we don't know how much power is being consumed by the load. We don't know the voltage, we don't know the current injection, but we know the generation part, how much power is being generated, and the voltage magnitude is as well. So therefore, we cannot directly use the Y-bus equations that we learned in the previous class, but we're going to utilize them, and I will show you how we have to use some iterations, but rather we must use the power balance equations. Now, power balance equations, we had this in the previous class as well, is basically Kirchhoff's current law. So we use KCL, which is Kirchhoff's current law, at each bus I. In an N-bus system, the current injection II must be equal to the current that flows into the network. And as you may recall, II is equal to IGI minus IDI. IGI is our generator, and DI is the load. So the total current in a bus, if we remember that we had a bus, is the generation, G, and the load, D, minus each other gives us II from the bus. Now, if we have multiple generators and multiple loads connected to a bus, we can expand it like sigma from K1 to N, I of IK. Now, since I is equal to Y bus V, or the admittance matrix times the voltage matrix, we also know that II is equal to IGI minus IDI. We can replace I with the equation YV. Again, as you remember, Y is 1 over Z. V is equal to IZ, the Ohm's law. In other words, V is equal to I over Y, or I is equal to YV. We had this in the previous class as well. So the network power injection is then equal to SI is equal to VI conjugate. Now, again, we can expand this, and when we expand it for multiple inputs, multiple loads, multiple generators, we get this SII VII conjugate and II is YV. So we replace that with YV, and we get VI sigma of K equal to 1 to N YI K conjugate VK conjugate. This is an equation with complex numbers. Sometimes we would like an equivalent set of real power equations. And these can be derived by defining Yi as Gik plus Jbik. Again, it's the conductivity admittance. And Vi is going to be Vi e to the power of j theta I, which is going to be Vi with a degree of theta I. And theta Ik is going to be theta I minus theta k. And as we recall, e to the power of j theta is going to be cosine of theta plus j sine of theta. Now, again, we can write this in the complex form, as mentioned previously. So we will replace Yik conjugate with e to the power of j theta ik, jik minus jbik. And if we expand that and resolve it, we get into the real and imaginary parts. The real part, Pi, is going to be sigma of K1 to N Vi Vk, the magnitude of Vi Vk, Gik cosine of theta Ik plus Bik sine of theta Ik, which is going to be Pgi minus Pdi. Now, theta I is going to be sigma of K from 1 to N Vi Vk, but this part is going to be Gik sine of theta Ik minus Bik cosine of theta Ik, which is going to be Qgi minus Qdi. Now, for power flow requires iterative solutions because we don't get a fixed solution. In the power flow, we assume we know Si and the bus admittance YB bus. We would like to solve for the V prime S. The problem is the below equation has no closed form solution. But rather, we must pursue an iterative approach. Now, we have different types of iterative approaches that we can use. One of the most utilized ones is the Gauss iteration. And as mentioned, we have different methods, like Gauss, Newton, and so on, Gauss-Rontgen, and so on. Now, with Gauss method, we need to rewrite our equation in an implicit form of x equal to h of x. The iterate, we first make an initial guess of x0, and then iteratively we solve for x v plus 1, which is going to be h of x v, until we find a fixed point x hat such that x hat is going to be equal to h of x hat. Now, I'll give you some examples. Now, for this example, we want to solve x minus square root of x minus 1. Now, if we solve it, we move this part to the other side of the equation. X is going to be equal to square root of x plus 1, or in other words, 1 plus square root of x that we have mentioned here. Now, x in the power of v plus 1 is going to be this x in the power of 1. Now, what we do, we would start from 0, let v equal to 0, and arbitrarily guess x0 equal to 1, and then we will solve it for v0, v1, v2, 3, and 4, 5, 6, 7, 8, and 9. Usually we don't go to the 9th iteration, we stop at 4 or 5. The goal is, you can see what happens after the 5th iteration. You can see the differences have become minimal, and after the 7th iteration, it's almost negligible. So for the first iterations, you can see that it quickly merges. So imagine that you have uh, like a graph, and what you want to do is you want to get to the answer. You can't get to the absolute answer, but what you can do is you can jump until you reach that answer. So the more iterations that you have, you're going to get closer to GOSA. And after a certain point, you get close enough that you don't care after that. You're just adding to the complexity and your uh, computational complexity. So after, let's say, fifth, now here after fifth iteration, you would see that the changes are not significant. So we can start around that and say the answer is 2.61185. In most situations, after fifth or sixth iteration, you're gonna get a fixed answer. In some questions, what we do is we say that you need to do only 4 iterations or 3 iterations and so on. So what we do, again, you just rewrite the equation and then you replace the numbers and you find it for each iteration. Now, for the first example, again, this quiz, I'm going to make it as a quiz. And mainly it's just for attendance. We want to use Gauss iteration to solve the following equation: x squared minus x minus 1 is equal to 0. We want to start with x in power of 0 is going to be 1, and find the first of x 0 is going to be 1, and find the first 4 iterations. Let's write your name for the first one then. Okay, has anyone solved it? Okay, do you want me to give you a little bit more time? Sorry, what? To the fourth, yes. This keeps cutting. Okay. Now, first thing we do, we have x2 minus x minus 1 is equal to 0. We rewrite the equation as x 2 is equal to x plus 1, or in other words, x is equal to, we would divide everything by x. Divide everything by x. It's going to be x is equal to 1 plus 1 over x. Now we would start at x of 0, the x0 iteration, which is going to be equal to 1 as mentioned here. And we would find the first 4 iterations. So x of v plus 1 is going to be equal to 1 over x of v. Now starting at the first iteration, x of 1 would be equal to 1 over 1 over x in the power of 0 is going to be what? 1. So it's going to be 1 plus 1, it's going to be 2. Now x of 0 is 1, x1 is 2, x2 would be equal to 1 plus 1 over x1, because this is going to be now x1 And what is x1? What is x1? The first iteration, 2. So it's going to be 1 plus 1 over 2 gives us 1.5. Now, the third iteration is going to be 1 plus 1 over x 2. Sorry, this is x1. Why did I put x1? So what is x2? 1.5, thank you. So this would be equal to 1 plus 1 over 1.5, which gives us 1.6667. Now, the fourth iteration is going to be 1 plus 1 over x of the third iteration, which gives us 1 plus 1 over, and what is the third iteration? Yes. So this divided by that, it's going to give us, can someone calculate this? Because I did it only to the third equation. It's going to be 1.6 something. Yeah, so I'm going to round it up to 1.6. Because 1.5999 something. It's going to be rounded up to 1.6. So it's pretty clear. You just find, you already have the first iteration, use that to find the second iteration, then the third iteration, and so on. So again, this is, by the way, x of 0, which is equal to 1. And then we have x of 1, which is equal to 2, which is equal to 2. Don't have to put it in. X of 1, which is equal to 2, and then x of 2, which is equal to 1.5, then x of 3, which is equal to 1.6667. Is it clear? We have to simplify it and, and make it like a linear, because we want to have a simpler iteration. That's the reason we rewrite it. We have to simplify it as much. If you want to do that, you're going to have two answers. It's going to be very difficult. Okay. Now, there is a key problem here that we need to address, is that when to stop the iteration, okay? Do we need to stop at 4 iterations, 5, 6, 10, 20? When the problem gets very complicated, we need to have a threshold, or I would say a boundary on when to actually stop the iteration. When is it good enough? We have to find the amount of error that we have, and sometimes we can't continue until 2,000 iterations, for example. You may not get to the final answer after 2,000 iterations. Sometimes you get to the answer after 5 or 10 or 20 iterations, but sometimes you don't get. So we need to need to set up when we want to stop the iterations. And we usually do that using this equation. With the Gauss iteration, we stop when delta x v, delta x subscript v is less than epsilon, and with delta x of v is equal to xv plus 1 minus xv. If x is a scalar, this is clear, but if x is a vector, we need to generalize the absolute value by using a norm, and this is going to be the J norm of delta x superscript v. It must be less than epsilon. And the common norms are the Euclidean and infinity. So we're going to have the 2 norm of delta x. It's going to be square root of sigma from 1 to n delta xi square. And the infinite norm of delta x is going to be equal to max of I of delta xi. Now, to find the Gauss power flow, we need to put the equations in the correct form. We need to find SI, and we need to find SI conjugate. Now for SI, we would have VI conjugate, and SI conjugate would be VI conjugate II. Now we write this as we did before. VI is fixed, we already know that. II, we can write it as an admittance matrix multiplied by the voltage matrix vector matrix. And for the first part, we get VI sigma of k from 1 to n, yi k conjugate, vk conjugate. And for the second part, we get VI conjugate sigma of k from 1 to n, yi k and vk. And finally, if you want to find VI would be equal to 1 over YII SI conjugate over VI conjugate minus the sigma of k from 1 to n, yik and vk. And I'll solve some problems for this as well. Now, an example, we have a 100 megawatt, 50 megavolt amp reactive load, which is connected to a generator through a line with an impedance of 0.02 plus J 0.06, and it's per unit, and line charging of 5 megavolt amp reactive on each end. It's 100 megavolt amp base. Also, there is a 25 megavolt amp reactive capacitor at bus 2. If the generator voltage is 1 per unit, what is V2? So again, we have a generator connected to bus 1 connected to bus 2 via this impedance that we have here, and we want to find V2. Now, first step we need to do, we have to convert all the impedances to admittance. And as you know, admittance Y is equal to 1 over Z. So we want to find Y bus, which is going to be 1 over 0.02 plus J 0.06. And if we divide that, we get 5 minus J 15. And this is going to be our Y12. It's the impedance between bus 1 and 2. So Y12, by the way, is equal to Y21. And it's going to be equal to negative of that Y12, or the Y between them, which is going to be negative 5 minus J, negative J 5 plus J 15. And we already know that B22 is negative J 15 plus J 0.05 plus J 0.25. Now, from the equation, V2 is equal to 1 over Y22. We have Y22, so it's going to be times S2 conjugate, V2 conjugate, because it's from the second bus, minus sigma of k from 1 to n, yik, vk. Now V2 is going to be 1 over 5 minus J 14.7 times negative 1 plus J 0.5 over V2 conjugate times negative 5 plus J 15 times 1 with a degree of 0 degree. Now we guess V2 0 is going to be 1 with a degree of 0, and we do the iterations. And if we do the iterations, you can see after the third iteration, we don't have any changes, so we can stop at this point. And at this point, we get V2 as 0.9622 minus J 0.0556. Now, we can convert that complex to a phasor or phasor mode. And once the voltages are known, all other values can be determined, such as the generator powers and the line flows. So in this case, S1 conjugate is going to be V1 conjugate, Y11 V1 plus Y12 V2, which gives us the power of the first bus. And by the way, this is all the impedances and generators connected to bus number 1, and we can do the same thing for bus number 2. For bus number 2, S2 conjugate would be V2 conjugate, Y22 V2 plus Y12 V1. Now, in actual units, P1 is going to be 102.3 megawatts. Q1 is going to be 23.9 megavolt amp reactive. And the capacitor is supplying a 23.2 megavolt amp reactive power. Now, to better understand this, I have broken down the next example into multiple questions, so it's going to be easier for you to solve. And this is going to be your next quiz question. A transmission line has an impedance of Z equal to 0.01 plus J 0.05 per unit. We want to find the series admittance Y equal to 1 over Z. Okay, did any of you?
J 19.23. 19.23, sorry.
Yes, that is correct. Thank you. Okay. So y is going to be equal to 1 over z, which is 1 over 0.01 plus j 0.05. There are multiple ways that you can solve this. You can convert this to, phasor and then divide it and convert it back. Just give me 1 second to see if I can fix. Just sorry, the screen has disconnected. Just give me a second. Let me continue. And so one way that we can do, we can multiply the denominator with the denominator with the complex conjugate. So what we get is going to be equal to 0.01 minus j 0.5 over 0.01 in the power of 2 plus 0.05 in the power of 2, which gives us 0.01 minus j 0.05 over 0.026. Now, if we divide each term, we get y equal to 3.846 minus j 19.231. See if I can fix the problem with my display. Just give me a second. Okay. So again, the answer is going to be 3.846 minus j 19.231. Now, for self-admittance, let's do another problem. We want to find the admittance here. We have a 2-bus system, and the line series admittance y line is 4 minus j12. Line charging at bus 2 is j 0.08. Shunt capacitor at bus 2 is j 0.2. And we want to find the self-admittance y22. So as a note, Y22 is the sum of, did you all solve it? Of all admittances connected to bus number 2. So Y22 is going to be negative J4 minus J12 plus J.08 plus J.2. Now what we do, we will combine the imaginary parts, and therefore Y22 is going to be 4 minus J12 plus J.28, or in other words, Y22 is going to be equal to 4 minus J11.72. That's it. Very simple. Now, the next thing is about slack bus. Now, in previous examples, we specified S2 and V1, and then we solved for S1 and V2. We cannot arbitrarily specify S at all buses because total generation must equal total load plus total loss. Kirchhoff's law. We also need an angle reference bus. To solve these problems, we define one bus as the slack bus. So this bus has a fixed voltage magnitude and angle and varying real or reactive power injection. So one bus is going to be our, let's say, benchmark, our base bus that we call the slack bus. And this bus has a fixed voltage magnitude and angle and varying real reactive power injection. Now, this is an example in a graph that shows our system. We have bus number 1, 2, and 3. And for this example, Y bus is J negative 15, 5, 10, 5, negative 15, 10, and 10, 10, negative 20. V is going to be equal to Y bus inverse I. Now, next example, a 90 megavolt amp reactive load is connected at bus 2 through a line with Z equal to 0.02 plus J 0.04 per unit on a 100 megavolt amp base. Ignore line charging and shunt capacitor. Bus 1 is the slack bus with V1 equal to 1.03 with a degree of 0. Use one iteration with a flat start of V20 of 1 plus J0, and we want to find V2 of 1. I'll give you a few minutes to think on it. So the first thing that we need to do is to convert the load to a per unit. So for per unit, what is the real power? It's 90 megawatt, and what is the reactive power? It's 40 megavolt amp reactive. So we will convert this to per unit, and it's a 100 megavolt amp base. So this is going to be 0.9 plus J 0.4 per unit. Okay. Now, for the bus equation, the injection power is negative of the load. So S2 is going to be equal to 0.9 minus J 0.4 per unit. And therefore, S conjugate 2 would be equal to negative 0.9 plus J 0.4 per unit. Now we want to find the admittance. We want to find Y, or the admittance. So Y would be equal to 1 over the impedance, which is 0.02 plus J 0.04. And if we calculate this, would be 10 minus J 20. Therefore, Y22 is going to be 10 minus J 20, and Y21 would be equal to negative 10 plus J 20. Now we want to apply the Gauss iteration equation. So V2, 1, will be 1 over Y22 S2 conjugate over V2 of 0 conjugate minus Y21 V1. Now, since V2 0 is the 0 iteration is going to be equal to 1, now we get S2 conjugate over V2 0 conjugate, which is 1. This is 1. Gives us the same, which is 0.9 plus J 0.4. Now we can calculate Y21 V1, which is going to be equal to S times its voltage, which is V1, which is 1.03. So this is going to be equal to negative 10 plus J 20 times 1.03 gives us 10.3 plus J 20.6. And from this would be equal to, yeah, if we want to do that, yeah, we want to, now we want to find this part. We already found Y21 V1, and we already have this. So combining them, we're going to have 0.9 plus J 0.4 minus negative 10 plus J 20.6, which gives us 9.4 minus J 20.2. So this gives us V2 of 1, which is equal to V2 of the first iteration. Oh, by the way, I'm sorry, this gives us this part. Forgot it one step. And then we have to divide it by Y21. So if I divide it by Y21, V2 of 1 gives us 9.4 minus J 20.2 divided by 10 minus j 20. So what we can do, we can multiply both the denominator and the denominator by 10 plus j 20 if we multiply it by that. V2 of 1 gives us 9.4 minus j 20.2 times 10 plus j 20 over 20 in the power of 2 plus 20 in the power of 2, which gives us 10 in the power of 2 plus 20 in the power of 2, which is 500. This is for the denominator. 500. And the denominator, if we multiply them, we get 498 minus j14. So therefore, V21 is going to be equal to 0.996 minus j 0.028. This is an example from the book, by the way, from the homework. Okay, so this is going to be V2. Okay, do you want me to go back so you can take a picture, or you're good? Okay, that's it for, I'm going to go back so you can take a picture. That's it for, and the previous one. That's it for today's class. If you have any questions, just please let me know. I would post some announcements. Just please keep an eye on your Canvas. And again, if you have any questions, just please let me know. Thank you so much.